Number 13, we have to figure out this integrals, the bounds for this integrals. So we are given this shaded region here, and since it has dx inside and then dy, having dx inside means that you're trying to go this way, because see, dx means this is increment in x direction. So you're going from left to right, because you're increasing the x direction, and you're beginning from the left end point to the right end point. So you somehow have to figure out the equation for the left line and the right line. The left line is easy. This is just a vertical line. Its equation is x equal to 0. So that's not hard. This one you have to figure out the line equation. Let's see how to do this. Well, this point here is 0, 1, and this point here is 4, 4. So in order to get the line equation, you need to know the slope, which is y2 minus y1 over x2 minus x1. It's change of y over change of x, right? It's 4 minus 1 over 4 minus 0. So it's 3 over 4. Then you select one of the coordinates to put it into the point slope form. The point slope form is y minus y0 and x minus x0. So you have y minus 1 equal to 3 over 4 x minus 0, and that simplifies to y equals to 3 over 4x plus 1. Now, however, when you try to figure out what the c and d is, notice that inside you have dx. That means these c and d has to be filled in with x equal to something. X equal to something. Okay. And this is okay. X equal to 0 is already in the form x equal to something. But this one here, y equals to 3 over 4 x plus 1, that's not okay, because this is not in the form of x equal to something. So you want to rewrite this as, let's see, y minus 1 equals to 3 over x multiplied by 4, so it's 4y minus 4 equals to 3x, and then you divide by 3, you get 4 over 3y minus 4 over 3. And now we have the equation in the form of x equal to something, and that's what you want to plug in. So you want to say now it's integral from x equal to 0 to x equals to 4/3 y minus 4/3. Okay, that's what you're integrating by dx. And then for dy, once you've done the integration from this line to the other line, then you now have to figure out the y value for the oh, by the way, when you have this outer integral, the last one should be numbers. Okay, you can never put x or y here at the last line. So never do that. Okay, so these two should also always be numbers. And what you want to put is, you want to put the maximum and minimum value of the y. So it goes from the minimum value of y to the maximum value of y, because you have dy here. So if you look at this domain, the minimum value is 1 and the maximum value is 4. So you should put 1, 2, 4. So the answer is, you have, let's see, d should be 4/3 y minus 4/3. C should be 0. B should be 4. And A should be 1. Okay, number 14. Okay, so you have this integral, and it says the integral is impossible to compute unless you change the order of integration. So this is a kind of integral that you have to change the order in order to solve. So let's try to change the order of integration. How do you do this? Well, you first have to figure out the domain of integration. Without drawing the graph, it's impossible to change the order of integration. This is in dx dy, so you need to change that to dy dx. Okay, first, since it has dx here, you should think of this as x equals to 2y and x equals to 4. What are those graphs? X equal to 4 is 4, and it's a vertical line, x equal to 4. X equals to 2y, if you solve this for y, it's 1/2 x. Y is 1/2 x, and that's a line with rise over 1 being 1 over 2. So if its run is 4, it should go up by 2. So this should be 4, 2. You can just figure that out by plugging in 4. 4 plugged in here, you get y as 2. Okay. And then, because this is dx, you're trying to go from this line to that line. You're trying to go right because dx is inside. If you have dx inside, you're trying to paint the region as you're going rightward. If dy was inside, you should be painting the region upwards. Okay, so it goes from this curve and to that curve. Now then it says for the y value, the minimum y value is 0 and the maximum y value is 2. So minimum y value is 0 and maximum y value 2. And as you're painting right, if you let your levels to be only between 0 to 2, you end up with this triangular region. So this is the region that you're trying to do. Okay. Now, in order to write the integral in terms of dy dx, you need to draw the domain, and then you try to go upwards. So that means you have to start from the bottom line and you have to end at the top line. Okay. The bottom line here is y equal to 0. That's just a horizontal line. Horizontal lines always have the form of y equal to some number, and in this case, since it's the x-axis, it's y equal to 0. Now this one we already know the equation. This is the same equation that we drew here. It's y equals to 1/2 x, and therefore you're trying to start at the bottom line, which is y equal to 0, and you're ending at this top line, which is 1/2 x. Okay. So you can put y or not, it doesn't matter. Y over x cosine pi over 3 x dy. And then now outside you have dx, and for these two you always have to put numbers. You can never put y or x. So you want to put numbers, and for those numbers you want to think about the minimum and maximum value of x. So the minimum value of x is 0 here, and maximum value here is 4. So it's from 0 to 4. Okay, now we've successfully changed the integral. Let's try to compute. If we integrate by y, this is an easy integral because y integrates to y squared over 2. So this becomes 0 to 4, 1/2 y squared times 1 over x cosine pi over 3 x. And then you have to plug in the endpoints 0 and 1/2 x. And then you have to do dx. Now these values here are for y because we integrated by y. You don't plug them into x, you have to plug into y. So instead of y, you have to replace 1/2 x. So let's do that. 1/2 x squared times 1 over x cosine pi over 3 x dx. And then when you plug in 0, when y 0 goes into y, it's 0, so you don't have to subtract anything. If this was something else, then you have to subtract. It gets more complicated. Alright, so now let's see, 1/2 squared is 1/4, 1/4 times 1/2 is 1/8. Let's bring that outside the integral, so that we have x squared times 1 over x times cosine pi over 3 x dx from 0 to 4, and then 1 over 8. X squared divided by x is just x, right? And cosine pi over 3x dx from 0 to 4. Okay. Now, that integral, so maybe I should write down step number 1, 2, 3, and then now 4. That integral is done by tabular integration or integrate by parts. You have to do either one of the two. I like to do tabular integration. So if you never have seen tabular integration, there's a video on my YouTube page that shows you some example. Since it's not easy to do integration by parts, you should definitely check that video out. It's only like a little more than 10 minutes, and you're going to get a lot of information out of it. Okay, so the tabular integration is plus minus d integral, and you put x here and cosine pi over 3x here, and then for these kind of column, it means you keep differentiating. X differentiates to 1, 1 differentiates to 0. Cosine, if you integrate sine, and one thing that you have to be careful is that every time you integrate, if there's something in front of x, the reciprocal of that number has to be brought up front. Okay. If you integrate sine, then you get negative cosine, so it's negative cosine pi over 3x. And again, because another 3 over pi comes, the reciprocal 3 over pi comes out, it becomes 9 over pi squared. And then the plus minus column is where the signs alternate, plus minus plus. Okay, and then you now do this. Looks like some missiles falling down, right? So go across and go down. Alright, that gives you the following result, the integral being x times 3 over pi sine pi over 3x. Okay, and then minus times minus plus, so it's 9 over pi squared cosine pi over 3x. Okay. You add them up, and that's it. Oh, by the way, the last line should also be multiplied and integrated, but integrating 0 doesn't do anything, so we don't care about that. So we only need these two. And then what you want to do is you want to now plug in the endpoints. So we plug in x times 3 over, actually, let's simplify this before plugging it. Okay. Okay. We're going to put 3 over pi x sine pi over 3x, pull the number in front, plus 9 over pi squared cosine pi over 3x. And then we have to plug in 4 and 0 and compute. When I plug in 4, what's sine 4 pi over 3? Sine 4 pi over 3 is, let's see, that's negative radical 3 over 2. And if I plug in 4 here, that's 12. Actually 4 divided by, okay, so it's going to be 6 radical 3 over pi if you plug in 4 here. Okay, and then if you plug in 4 here, cosine 4 pi over 3 gives you negative 1/2, so it's minus 9 over 2 pi squared. Okay. And then when you plug in 0, this is 0, whereas this one, if you plug in 0, it's 9 over pi squared. And you have to subtract. So the final answer is, if you simplify this, the final answer is let me put number 5 here. I'm all over the place. Okay, the final answer is it's 6 radical 3 over pi minus let's see, this is if I make common denominators, you have to multiply 2 top and bottom, so it's 18, so it's minus 27 over 2 pi squared. So that's the answer. It's a little weird. Okay. Here it says the region R is a triangular region whose vertices are 0, 0, 1, 1, 1, 0, 2. So let's see. Let's draw the domain. 0, 0, 1, 1, and 0, 2. Oh, I see. 0, 2. So it says triangular domain. Alright, and I have to find the volume under the graph of the function. Basically, the graph of the volume under the graph of the function is you integrate over the given domain fxy dA. That gives you the volume. This is what we want to compute. And since dA could be written as dy dx or dx dy, you have to choose. But I see that if I choose dx dy, then I'm trying to go from left to right, and that gives you some complication here because before 1, less than 1, you're following this as your right endpoint, but after 1, you're on here. So if you try to use dx dy for this region, you'll see that because of the shape of the domain, you'll end up with 2 integrals. However, if you use dy dx, it's going to be just 1 integral, so it's probably easier to do dy dx. So let's try dy dx. Okay. So if I choose to do dy dx for our dA, then I'm trying to paint it upwards, going upwards. That means I have to start from this line, and I end at this line, right? So let's see, what is this line? This is just y equal to x, isn't it? Because it passes through 1, 1 and 0, 0, so that's what it is. That's easy. What about this one? This one has a slope of -1 because it's 45 degrees going down, and its y-intercept is 2, so it's -x plus 2. Okay, so that's this one. Okay, and then now we have you start from y equal to x, and you end at -x plus 2 of 3x plus 2y dy, and then you integrate with respect to x. X goes from 0 to 1 because that's the minimum value of x. So 0 is the minimum value of x when you're on the left, and the maximum value of the x coordinate is when you're here, which is 1. Okay? So that's the minimum and maximum value of x. Okay, now let's continue. If I integrate this by y, it's 3xy plus y squared, and I have to plug in -x plus 2 and x. I still have to integrate it by x, 0 to 1. Okay, and then these should go into y only because we integrated by y. So -x plus 2 plugged into each one of these, you get 3x, -x plus 2, plus negative x plus 2 squared minus, and then you plug in x into y, so it's 3x squared plus x squared. Okay, and we have to simplify this and integrate by 0 to 1. Okay, alright, so let's continue. 0 to 1. This is negative 3x squared plus 6x. If you expand this, this is going to be x squared minus 4x plus 2. And then this is 4x squared, so you subtract 4x squared. And let's see, that's negative 3 plus 1 minus 4 is negative 6x squared. 6x minus 4x is 2x. And then you have 2 dx, which is negative 2x cubed plus x squared plus 2x, and you plug in 0 to 1. So if you plug in 1, it's just 1. If you plug 0, it's 0. So it's 1. That's the answer. Alright, next. Change the following equations into polar coordinates. Now, you have to know how to go back and forth between polar and rectangular, and basically this picture explains everything. If you have something in rectangular, then your x-coordinate is this length. So for this point, your x-coordinate is this length, and your y-coordinate is this length, right? And if you try to express this point in terms of r and theta, r is this distance, and theta is this angle. That's what the definition is, right? Now from here you can easily see that x must be r cosine theta, and y must be r sine theta. And also the Pythagorean theorem says that r squared is x squared plus y squared. And then finally, if you want the theta, you need tangent inverse of y over x, just from SOHCAHTOA. Okay? Tangent is opposite of adjacent, so opposite of adjacent is y over x. And then you have this annoying plus alpha, where depending on your quadrants, it's 0, 0 on the right side, but it's pi. You have to add 180 degrees on the second quadrant, and in third quadrant you have to subtract 180 degrees. So that's like the basic formulas that you have to know. Now among these, when you're trying to change a rectangular equation into polar, you just have to mainly apply the first two. You just replace y by r sine theta, and then x by negative r, x by r cosine theta, so it's negative r cosine theta. Let's see, and then you want to solve for r, but see, if you can divide by r, you can just cancel the r, because see, in polar coordinates, r equal to 0 is just the origin, and usually that doesn't play any role. So when you can divide by r, both sides just divide, and then you have sine theta equal to cosine theta. Now that's a little strange, right? But if we divide cosine theta both sides, we have sine theta over cosine theta equal to 1, which is tangent theta equal to 1. And you've seen this somewhere. When is tangent theta equal to 1? When theta is equal to 45 degrees, right? The tangent of 45 degrees is 1, so theta is pi over 4. So you actually get just a single expression, theta equal to a number. And if you think about it, it makes sense, because if you collect all the points on the plane that has 45 degrees, it's actually these points, right? Every point on this 45 degree line actually has 45 degrees from this positive x-axis. So yeah, so is exactly what you're looking for. All right, B, you have y equal to x squared plus x. Do the same thing. It's r sine theta, r squared, cosine squared theta, and then r cosine theta. Okay, now again divide by r because you can. And then see, after dividing by r, this time we still have an r left. So that means we can solve for r. So let's do that. Move the cosine to the other side, so you get r cosine squared theta equal to sine theta minus cosine theta. So I move the cosine to the left side and switch to left and right. And now I divide by cosine squared, sine theta minus cosine theta over cosine squared. Okay, so this is perfectly good. However, if you want, you can kind of try to simplify this. This is a sine over cosine squared, which is like sine over cosine times 1 over cosine. And cosine over cosine squared, that's just 1 over cosine. Sine over cosine is tangent theta, and 1 over cosine is secant theta, and then 1 over cosine is secant theta. So that's another way to express it. Okay, r is tangent theta, secant theta. Okay. Now for c, I see x squared plus y squared. Oh, that's this one, right? X squared plus y squared is r squared, so I can rewrite it as r squared minus 6x is now r cosine theta. Divide by r, so you get r minus 6 cosine theta equal to 0, and then you solve for r. R is 6 cosine theta. Okay. That turned out to be easy. But it's going to be a little bit longer if you don't use r squared equal to x squared plus y squared, and rather use x equal to r cosine theta and y equal to r sine theta plugged into x squared and y squared. It's just a slight bit longer, so you probably want to use r squared equal to x squared plus y squared whenever you can. Okay, find the area of 3 petal rows r equals to 8 times cosine 3 theta. Let's see. This here, cosine 3 theta, is a 3 petal rows because, think about the following. Just think about the case when 3 theta becomes one of these important values like 0, pi over 2, pi, 3 pi over 2, and then 2 pi. Let's see. If you solve for theta, it's 0, pi over 6, it's pi over 3, and then pi over 2, and then what's that? 2 pi over 3. And then for that, what's cosine 3 theta? Cosine 3 theta is cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 is 0 again, and cosine of 2 pi is 1. And if you multiply by 8, 8 cosine 3 theta is 8, 0, -8, 0, 8. Okay. Now, for all these calculations, you really want the following too. I want this, and also this, because r is equal to 8 cosine 3 theta, so r value is given by these. Okay? So what you're trying to do is you want to plot 8, 0, 0, pi over 6, -8, pi over 3, and then 0, pi over 2, and then 8, 2 pi over 3. See, what I did was I just paired each r values with the theta value. Okay. Okay, so let's try to plot that here. So at angle 0 degrees, you have to go out till 8. So that's where you begin. And then angle 30 degrees, pi over 6 is 30 degrees, so think about this. Pi over 6 degree and the curve should be hitting the 0 at this angle. So it starts from 8 and it goes down and hits the 0 like that. Okay, and then at pi over 3, where's the pi over 3? This is pi over 3, 60 degrees. You're reaching -8, so you're here. Here's -8. So you should reach here. Okay, so go like that. And then if you go to 0, comma pi over 2, pi over 2 is here, and you're hitting the 0 at this angle, so you have to come back and hit the 0 here. And then 2 pi over 3 is this one. That's 2 pi over 3. And you have 8, so here's 8, so you have to hit this. Okay. Alright, so you can continue this to draw out the curve, and you'll see that at pi you complete one full graph. Okay, so you rotate around this 3-petal leaf from 0 to pi. Okay, so from theta equal to 0 to pi, you complete 3-petal rows. You may remember that if this number is odd, then it's the number of petals is the same. If not, this number in front of theta is even, then the number of petals is twice. So for example, if you had cosine 2 theta, you would be looking at rows with 4 petals. But if it's cosine 5 theta, it's rows with 5 petals. And another thing is, if this number is even, cosine 2 theta or 4 theta, then the entire graph is completed in 0 to 2 pi, not 0 to pi. However, if it's a cosine odd number times pi, the entire graph is completed from 0 to pi. So you just have to integrate from 0 to pi to get the area of the 3-petal rows. Now, if this is all confusing, an alternative way to do this would be just first draw from here to there and realize, hey, this is like this is like half a petal, right? So if you know that this is 3-petal rows, then you first just integrate from theta from 0 to pi over 6, whatever, and then r d theta, and then you double this to make a full petal, and then multiply by 3 because you know that's 3-petal rows. And actually, this is not too bad. You can try this. Okay, but for us, we will just continue it this way. All right. So how do we compute the area? We have to compute the area. You have to integrate on this 3-petal rows. On this 3-petal rows 1 dA. If you integrate 1 over a region, then it gives you the area of that region. And then if you convert to polar integration, dA should be written as r d theta. And theta is easy because we just figured out that theta should be from 0 to pi. What's not easy is dr. What should we do with dr? So for dr, you have to think about painting this region radially, because dr here, dr is increment in r direction, right? So you're increasing in the r radial direction. So you start from 0 and you reach the curve and you end. Right? So you start from 0, which is the origin, and you reach the curve, which is 8 cosine 3 theta. Then you get the area. All right, so let's continue. 1 times r is r, and if you integrate r by dr, you get 1/2 r squared. And you have to plug in 8 cosine 3 theta, and 0, and then 0 to pi 3 theta. And then when this goes in, 8 squared is 64, and divide by 2, that's 32. Cosine 3 theta squared. And then when you plug in 0, there's nothing. 0 gives you 0. So you have to integrate this from 0 to pi 3 theta. Okay. Now when you're integrating even powers of sine and cosine, you need to use the following formula, which is cosine squared of a is 1 plus cosine 2a over 2. And there's another one for sine squared, right? Sine squared is 1 minus cosine 2a over 2. So if I apply that, I get 0 to pi 32, 1 plus cosine. Well, if a is 3 theta, 2a is twice of 3 theta, which is 6 theta. And then 32 divided by 2 is 16, so if I pull the 16 outside, it's from 0 to pi of 1 minus 1 plus cosine 6 theta 3 theta. And then if you integrate 1, that's theta. If you integrate cosine 6 theta, it's plus 1/6 of sine 6 theta. You have to take the reciprocal of this 6 and put it in front. And then 16, and then you plug in pi and 0. If you plug in pi to theta, it's pi. If you plug in pi, sine 6 pi. Sine of any integer times pi always gives you 0. So it's going to be 0. If you plug in 0, both of them gives you 0. So you end up with 16 pi as your answer. Okay. So maybe I should do this. Alright, so here we have a rectangular integral where you have to sketch the domain and change the polar coordinates and complete the integral. Alright, so let's try this. First, you have dy, so you have to think about the two bounds as y equals to square root of 4 minus x squared and y equals to negative x. Now, for this one, this is actually almost same as y squared equals to 4 minus x squared, because if you square both sides, the square root goes away. And then if you move the x squared to the left side, you get x squared plus y squared equals to 4. And that you recognize as a circle. Oh, I shouldn't have shaded it, sorry. So let me do this again. It's just a circle of radius 2. However, because the original one has square root of 4 minus x squared, in the original equation y cannot be negative, it can only be positive, so it only gives you the top half of the circle. Okay. Now everyone knows y equals to negative x, so let's think about this. Okay, so these are the graphs, and then you put them together, top half with this y equal to x, and you say, you start from this curve, the 45-degree line, and you end at the top circle, and you're going upwards because it's dy is inside. Now look at the bounds for x. It's from negative radical 2 to 0, right? And if you check, you can check that the point where these two meet, negative x equal to square root of 4 minus x squared, the point where these two graphs meet is actually at negative or equal 2. So let's do that. If I square both sides, it's x squared equal to 4 minus x squared. Moving the x squared to the other side, you get 2x squared equal to 4. So x squared is 2. So x is plus minus right equal 2. But because, I mean, the two graphs meet at something negative, right? So you just get x equal to negative right equal 2. The reason that you get this fake solution plus right equal 2 is that sometimes if you solve radical equations, you get fake solutions like that. You have to go back to check that this is not a solution. Plus right equal 2 is not a solution. You can plug it back in and see that it's not. Okay, only negative right equal 2 is the solution to this equation. So that's where they meet. Okay, and then inside these bounds, minimum and maximum value of x is negative right equal to 0, and you go from the bottom to top. So you paint this region. Okay, so that's the region that we're. So the answer to A is that it's this circle, 45 degrees. This is the region. Okay, it's circle radius 2. Negative, actually, 3 pi over 4. 135 degrees from the from the positive x-axis. Okay. All right. Change to polar coordinates. So let's try to change this to polar coordinates. Okay. First, see, square root of x squared plus y squared. That reminds you of this formula, r equals to x squared plus y squared square root. Because of this, you can rewrite that thing inside as r. And then dy dx is r dr d theta. Okay? So that's so maybe these are something that you should definitely remember. Okay, what about the theta? Theta goes from pi over 2, which is the 9 degrees, until 3 pi over 4. So you should put pi over 2 to 3 pi over 4. And then dr, well, if you try to paint this region radially, because dr means it's increasing the r direction, then you start from 0 and you end at this circle, which is this circle is r equals to 2, because r equals to 2 gives you this circular radius 2. So you start from 0 and you end at 2. Okay, now if you look at this integral, the result is pretty good, because the original integral, although it's possible to do the integration, it's quite hard. It's not so easy. However, the one that's transformed into polar coordinates, this is very easy to integrate. So let's actually do the integration. That's part C. R times r is r squared, and if you integrate r squared, it's 1/3 r cubed. And you plug in 0 to 2. And then when you plug in 2, it's 8 over 3. So that's 2 over 4. And this is 8 over 3 d theta. So 8 over 3 theta, and you have to plug in pi over 2 until 3 pi over 4. Okay, and then when 3 pi over 4 goes in there, that's 2 pi. Right, 2 pi. When pi over 2 goes in there, that's 4/3 pi. And 6 over 3 minus 4 over 3 is 2 over 3, so 2/3 pi is the answer. Okay, let R be the tetrahedral domain in the three-dimensional space whose vertices are. Okay, so that's a little hard to think, but let's try. I think in 3 dimensions. Here is x, y, and z. Okay, so first 0, 1, 0. What does that mean? I move one step to the y. That's what it is. Okay, maybe I should use a different color here. So that's 0, 1, 0. And then okay, I think I've left out something. Tetrahedron has 1, 2, 3. Oh, okay. I thought there was something wrong with the question. Sorry. So, okay, 0, 1, 0, 0, 3, 0. What's that? 0, 3 is here. 0, 3, 1. Okay, so from 0, 3, 0, 0, 3, 1 is just one step going up. Okay. And then 1, 3, 0 is from 0, 3, 0 is just one step to the x direction. So you have this right triangle, and you have this. Okay, good. All right, so this is what you're trying to integrate over. And because you have dz inside, you're increasing up. So you have to figure out what's the bottom surface of this tetrahedron and what's the top surface of this tetrahedron. Note that this line here is a vertical line. It's a vertical line. And therefore, maybe I should put this as a blue one. Okay. And therefore, really, you're starting from this triangle in the bottom, and you're ending at this other triangle that's on this side, on top. The bottom surface is easy to think. It's just the xy plane, since this is the xy plane. That's z equal to 0. Okay, so that's not a problem. The top surface, however, is the point. This one here is a plane passing 0, 1, 0, 0, 3, 1, and 1, 3, 0. Okay, it has to pass through those 3 points. Now, in that case, I need to, let's see, 0, 3, 1, 1, 3, 0. Okay, I need to find 2 vectors and do cross product to know the normal vector. Yeah, this is a long question. Okay. All right, so let's find one vector. V is 0, terminal minus initial. So it's 0, 2, 1. And let's say U is terminal minus initial. It's 1, 3, 0. And let's also subtract 0, 1, 0. So it's a 1, 2, 1. Okay. And the normal vector is the cross product. It's V cross U. Or you could do U cross V. It doesn't matter. At the end of the day, it's going to be the same answer. So I have I, J, K, 0, 2, 1. Oh, sorry, this is 0, 1, 2, 0. 1, 2, 0. And then for I, you have 2 times 0 minus 2, so it's negative 2i. And then J, you have 0, minus 1, but j has a minus, so it's plus j. And for k is 0 minus 2, so it's negative 2k. Okay, so that's the vector. And then you say negative 2, x minus 0. I'm choosing this as my 0, 1, 0 as x naught, y naught, z naught. So you have negative 2 plus y minus 1 minus 2 z minus 0 equals to 0, which means that the top equation is negative 2x plus y minus 1 minus 2z equal to 0, and then you solve this for z, you get negative 2x plus y minus 1 equals to 2z. So you get z equal to, let's see, if you divide by 2, it's negative x plus 1/2 y minus 1/2. Okay, so that's the plane on the top. Okay, so that means that when you do e to f, f should be negative x plus 1/2 y minus 1/2, and e should be, where is e? E is 0, okay, because you start from 0 in the end there. Okay, so that's the answer for f, which actually required quite a long calculation. Now let's go to the other parts. Now for the other parts, it's now easy, because once you integrate over z, it has the effect of just flattening down everything onto the xy plane. So on the xy plane, this is what we see. See, this 0, 1, 0 is now just 0, 1. 0, 3, 0 is 0, 3. And 1, 3, 0 is 1, 3. So if you take these 3 points, which are already on the xy plane, and then just ignore the z coordinates, then you can see what that bottom triangle looks like. And that triangle is what you're going to get if you flatten the entire object down to the xy plane. So that means now I have to describe this region with using dy dx, meaning that I have to try to paint upwards. Okay. Alright, so now I know what the top equation is. That's just y equals to 3. The hard part is, what's this equation? 1, 3, and 0, 1. What's the slope? That's you go up by 2 and you rise is 1, so slope is 2. You can see this, the slope is 2, and the y-intercept is 1, so you can easily find out the equation for this bottom one is y equals to 2x plus 1, and therefore when you have c to d, c is 2x plus 1 because you start from this bottom line, and at d it's y equals to 3, so that's what you get. And finally, from a to b, you just have to now put the minimum and maximum values of x. Minimum value of x is 0, maximum value of x is 1. Okay. Number 20. Convert the following integral to both cylindrical and spherical coordinates and evaluate the simplest one. Okay. So this one, if you look, you have this z equals to negative square root of 16 minus x squared minus y squared. Now this is a sphere. This is bottom half sphere. To see that, if you square both sides, z squared equals to 16 minus x squared minus y squared. Negative disappeared if you because you squared, and move the x squared and y squared to the left. So you get this sphere of radius 4, right? This is a sphere of radius 4. But if you go back to the original one, you see that z can only be a negative value, so you just get the bottom half sphere. So what you're getting is you're getting this bottom half sphere of radius 4. However, you're not considering the entire bottom half sphere, you're only considering over this domain. Let's see what this domain is. This domain here is y equals to square root of 16 minus x squared. Is just the top half circle. And if you treat your x values to be from -4 to 0, then you're only playing with this much. Okay. Then, let's see. So on here, if I use x, y, and z, you're really getting from this quarter of the bottom half sphere. So it's a 1/8 of a sphere, but it's just this much. Okay. All right. Now let's try to change this into cylindrical. Cylindrical is easier than doing a spherical because you're really basically trying to take the two-dimensional picture and change it to polar. And in that picture you see that the angle go from pi over 2, 90 degrees to 3 pi over 2, right? This is pi over 2, and this is, oh, not 3 pi over 2, so it's pi. 3 pi over 2 to pi. And then your r value goes from 0 to 4 because that's the circle of radius 4 centered at the origin. And then the z is the same thing, except you have to replace x squared plus y squared as r squared. See, r squared is x squared plus y squared, so instead of subtracting x squared plus y squared, you can subtract r squared to 0. And then x in cylindrical coordinates is r cosine theta, so you replace it like this, and it's r dz dr d theta. Okay. So remember, you need to know the following two formulas. Maybe I'll write right here. dv is r dz dr d theta, and in spherical it's rho squared sine phi d rho d phi d theta. Okay, so that's your cylindrical coordinates. Now let's go to spherical. Now in spherical, at least d theta is the same thing, so you don't have to worry about it. Just copy it from the cylindrical. But now you have to think about what to put for phi and rho. Okay, so for phi is the angle from the North Pole. So if you start from the North Pole and you try to go down until you hit this region, you see that this angle is 90 degrees. Okay. So you start from pi over 2, and then you go down to the South Pole, which is pi, and then sphere of radius 4 is 0 to 4. Okay. All right. So that's how to represent the domain. Now let's see. R is rho sine. Rho sine phi. And then r dz, this much, is changed to rho squared sine phi d rho d phi d theta. Okay. So let me make just a quick remark here. For spherical coordinates, this picture is important, where if this is a z axis, the angle from the North Pole is phi. That's called phi. And if this is the point that you're trying to represent from the origin, the distance from the origin is called rho, whereas distance to the z-axis is called r, and the height of this point is called z. So from here we have the important formula that z is rho cosine phi, whereas r is rho sine phi. So these two are needed in order to convert things into spherical coordinate system.